figure is of a thin and uniformly charged positive rod. We want to calculate the electric field strength at a distance d in the plane that bisects the rod. To begin, we must set up a coordinate system where the plane that the point P is on to the center of the rod. This gives us an x and y axis to work with. Here, we mark L as the length of the rod, and L over 2 being the top of the rod, and negative L over 2 being the bottom of the rod, considering our origin, and D, the distance between the rod and point P. Next step is to divide the rod into several small segments, which we will be able to use as point charges, with length delta y and charge delta q, which is equal to lambda, which means charge density, and delta y. Now, we draw the specific field lines that intersect P. These lines are exactly the same distance from the origin. Because the lines are the exact distances from one another, we know that the EY components cancel, leaving us only with EX values to work with. To solve the problem, we must recognize each segment of the rod as a point charge. This gives us the equation E sub 1x equals E sub 1 cosine of theta equals k times delta q divided by r sub I squared times cosine theta, k being the constant 9 times 10 to the 9th, and r sub I being the distance from charge I to the point P. Using the Pythagorean theorem, we find that Ri equals the root of y sub I squared plus d squared. Cosine of theta equals d divided by ri, which equals d divided by square root of y sub I squared plus d squared. After plugging in, we find that E sub I of x equals k delta q times d divided by y sub I squared plus d squared to the 3/2. Now we must change this equation into a sum to account for every single electric field line going through P. We find that this equals E sub x equals the sum of, from I equals 1 to infinity of E sub ix equals k times the sum of from I to 1 to infinity times of d delta q divided by y sub I squared plus d squared to the 3/2. Delta q equaling lambda delta y, and lambda being charge density, which equals q over L, and therefore delta q equals q divided by L delta y. Now, we must substitute q over L delta y for delta q to make our equation integral friendly to find our answer. This gives us E to the sub x equals k times q over L times the sum of I equals 1 to infinity times d delta y divided by y sub I squared plus d squared to the 3/2. Now, we turn our sum into an integral. This change causes delta y to be delta y, mean dy, giving us E sub x equals q divided by L times k times the integral from negative L over 2 to positive L over 2 times d multiplied by dy divided by y squared plus d squared to the 3/2. Integrating, we get that E sub x equals q divided by L times k multiplied by y divided by d times the square root of y squared plus d squared from negative L over 2 to positive L over 2, which equals k divided by L times k multiplied by L divided by 2 divided by d times the square root of L over 2 squared plus d, all take away negative L over 2 divided by d times the square root of negative L over 2 squared plus d squared. This all equals k times the absolute value of q, because q was the positive charges on the positive rod, divided by d times the square root of d squared plus L over 2 squared.